In my previous video, I repaired an old electron microscope and produced some really cool images. However, if we want to justify having a SEM, then it really needs to outperform an optical microscope. When this machine was new, it could magnify up to 200,000 times and resolve details down to 5 nanometers, about 100 times better than the best optical microscopes. However, like any delicate machine, performance degrades without proper maintenance, and this SEM hasn't had a tune-up in over a decade. The first step in that process is having the correct tools for the job. Today, I'll be building the most important tool for the task: a gold nanoparticle resolution test target. Okay, so what is a gold nanoparticle resolution target, and why do we need one for the SEM? Well, simply put, a resolution target is anything you can use to test the maximum resolving power of an imaging system. For cameras, we use something like this. What we need is a similar test pattern for the SEM. This will allow us to determine the exact resolution of the microscope to see if it's performing up to its rated specs. It will also allow us to compare its performance before and after any tweaks or repairs. Lastly, it will allow us to calibrate the microscope, but I'll go into a little more detail about that in a moment. Okay, so how do we take this test pattern and shrink it down small enough so that it's useful in an electron microscope? Well, we can't, but not for the reason you might think. The main issue is contrast. You see, we chose black and white bars in our camera test because black and white are the two colors with the highest contrast in an optical system. If we, say, chose gray and a lighter gray, then it would be much harder to see the lines, and this would affect our ability to run the test accurately. The problem is, an electron microscope isn't an optical system. It's not using light to make the image, so black and white bars won't show up at all. In an electron microscope, contrast primarily comes from one of two places. The first is topography. This is a sample of carbon powder. The individual flakes and grains are visible in detail because the number of electrons picked up by the detector depends heavily on surface topography. The second source of contrast is material density. Here is a sample of material that has been cut and polished smooth, so there is zero surface topography. This sample actually contains several different materials, and the details visible in this image are due almost entirely to the difference in density between those regions. Generally, regions consisting of small atoms, such as carbon or silicon, appear dark, and regions consisting of larger atoms, like iron or copper, appear brighter. This means that if we want to maximize the contrast in our resolution target, we want to choose two materials that are as far away as possible on the periodic table. For this reason, it's common to use carbon, element 6, as the low-density portion of our image. For the high-density element, we need to choose something that isn't radioactive, so everything above lead is out. Gold is non-toxic and extremely chemically stable, so gold is an excellent choice for this task. Okay, so ideally we want to make our test target with alternating gold and carbon regions. Now, lines would be fine, but remember, we're doing this for a scanning electron microscope, so any features we make have to be tiny. And unfortunately, my multi-million-dollar EUV lithography machine is in the shop right now. Fortunately for us, spheres can actually accomplish the same task. Ideally, we'd make spheres in a broad range of sizes. That way, all we need to do is find the smallest spheres that are still in focus, and that gives us a repeatable measurement for the ultimate resolution of our microscope. And conveniently enough, nano-sized gold spheres can actually be made using relatively simple chemistry. The spherical shape also has an added benefit. It allows us to calibrate the microscope. Let's talk about that. In an optical microscope, you bring the image into focus by adjusting the distance between the objective lens and the specimen. This requires turning only one knob. By contrast, on an electron microscope, image sharpness is dependent on proper calibration of the electron beam. And unfortunately, calibrating the electron beam is a complicated process, requiring many different adjustments. You can see on the control panel how many different knobs there are to adjust the electron beam. And believe it or not, this SEM is actually an entry-level model, lacking some of the controls that exist on high-end electron microscopes. So when using an SEM, if your image is out of focus, it can be hard to determine exactly which knob to turn to fix it, especially when your sample is visually complex. This is where the gold nanoparticles come in handy. Their simple geometry makes it very easy to calibrate the electron beam, at which point you can simply move over to your complex specimen knowing that your beam is properly adjusted. Okay, so we've established exactly what we want. We want gold nanoparticles of different sizes on a carbon background. So how do we get that? Well, you can just buy them. Ted Pella, a supplier of electron microscope accessories, happens to sell exactly what we want. So the obvious question is, why don't I just buy one? Well, there are two reasons I want to make them myself. First off, as you might expect, these calibration targets are very expensive. Ted Pella charges over $200 each, which is nothing for a well-funded lab, but not exactly a hobbyist-friendly pricing. In addition, I happen to know a bunch of other hobbyist SEM owners now, and so if I can figure out how to make these, then I can save each of them $200 as well. The other reason I want to make them myself is the issue of size. You see, modern electron microscopes can resolve details down to 1 nanometer. For a hobbyist restoring an old electron microscope, however, it's not uncommon to start off with a very poor resolution in the micrometer range or worse. A lab-grade calibration target might simply be too small to be useful. So I want to make a calibration target that covers a much larger range, specifically suitable for electron microscope hobbyists. Okay, so how do we actually make this? Let's start with the background first. Now, the correct way to do this would be to deposit carbon onto a silicon substrate using a thermal evaporator. However, my thermal evaporator is in the shop right now. What if I just use silicon instead? These silicon chips I have in abundance were polished until they're almost atomically smooth. Now, silicon isn't carbon, but it's still low enough on the periodic table that I think it will serve as a suitable background. So let's go ahead and use that for now while we focus on the much more interesting problem of creating the gold nanoparticles. Now, with a name like gold nanoparticles, you may think that making them is a relatively new invention. But actually, gold nanoparticles have been used to make red stained glass since at least the Middle Ages or earlier. The basic recipe is simple. You start by dissolving the gold in an acid called aqua regia. This converts the gold into something called chloroauric acid. Then you add another chemical, called a reducing agent, which converts the chloroauric acid back to elemental gold. This conversion causes the dissolved gold to fall out of solution so quickly that it doesn't have time to form large particles. The particle size is usually between about 10 and 100 nanometers. There's just one hang-up though. Gold particles aren't soluble in water, so over time they'll just settle to the bottom of the container. Fortunately, there's a clever trick we can pull to keep the gold dispersed in solution. If we bind the gold particles to an ion that is itself soluble, then the ion will be attracted to the water, and the gold will be forced to come along too. So even though the gold itself isn't soluble, the gold and ion combo is. What's even cooler is that because the ions are electrically charged, the gold nanoparticles in solution will repel each other and stay separated. Without the ions, the gold particles would eventually run into each other, and interatomic forces would cause them to stick together and quickly become a massive clump. With the ions, though, the gold particles will stay separated basically indefinitely. Pretty cool. Okay, so I think, finally, we've laid out everything we need to make this work. We need gold, aqua regia to dissolve the gold, a reducing agent to precipitate the gold, and an appropriate ion to bind to the gold. So let's start with the gold. Unfortunately, my powers of alchemy are not sufficient to make gold from nothing, so I had to purchase some. This is a 1 gram bar of gold I bought from the local coin dealer. Current prices are around $100 a gram, which is a lot, but this amount of gold is enough to make thousands and thousands of these test targets, so I'm not really upset at the price, assuming I don't accidentally lose it somehow. Okay, now let's move on to the aqua regia. Gold is a chemically inert material, and it's resistant to almost all acids. However, a combination of hydrochloric and nitric acid is strong enough to dissolve even noble metals like gold. Hydrochloric acid is relatively common and is sold as a pH reducer for pools, so that's where I decided to start. However, I immediately realized a problem. The hydrochloric acid I bought was yellow, indicating it has other stuff in it. I have no idea what they added, but whatever it is likely to interfere with our reaction, so it has to go. The easiest way to purify hydrochloric acid is to distill it, so I set up an apparatus to do just that. When heated, the hydrochloric acid should boil out and leave the impurities behind. The purified vapors will be condensed and collected in a second vessel. Now, HCl vapors are highly corrosive, so it's important to direct any excess gases into a trap. I'm using an inverted funnel in a beaker of water mixed with sodium carbonate for this purpose. Any excess HCl vapor will end up dissolving in this water and reacting with the sodium carbonate, producing sodium chloride, table salt, and carbon dioxide. The trap is good, but I'm still using good ventilation and wearing a full face mask because acid vapors are no joke and there's always a chance something will go wrong. And, spoiler alert, something did indeed go wrong. I turned on the hot plate and waited for the acid to come up to its boiling temperature of 108 degrees C. However, before it even got to 100 C, it started producing a ton of hydrogen chloride gas, which quickly began to overwhelm the sodium carbonate trap and leak out into my lab. What in the world is going on? Well, here's the mistake. You see the container here? I misread this as 20% HCl, when in reality, it was 32%. Oops. This is the problem. You see, hydrochloric acid at 30% concentration will fume violently and release hydrogen chloride gas when heated. At 20% concentration, that fuming is minimal. Had I realized my HCl was 30%, I would have diluted it down to 20% straight away. Oh well. Instead, I just ended up venting the extra gas into my lab. Not ideal, but hey, this is why you always wear PPE, I guess. Finally, the distillation finished, and I had about 200 milliliters of squeaky clean 20% hydrochloric acid ready to go. Alright, one acid down, one to go. Unlike hydrochloric acid, nitric acid is a bit tougher to purchase as an amateur. It definitely is available on some sites, but buying it is pretty sketchy and expensive. Fortunately, it's easy to make. The most common route to make nitric acid is to heat a mixture of an acid, a nitrate salt, and water. Most commonly, it's sulfuric acid and sodium nitrate. You can also swap out the sulfuric acid for sodium bisulfate, which is cheaper and more easily accessible in some places. I decided to try the bisulfate route this time. I mixed stoichiometric amounts of sodium bisulfate and sodium nitrate in my flask with just enough water to fully dissolve the solids, and then set up for another distillation. I turned on the hot plate and waited for the reaction to start. As the bisulfate and nitrate react, they form nitric acid, which boils out and condenses into the receiving flask. Now, I've tried the sulfuric acid method before, and it's pretty straightforward to get good results. The bisulfate method, however, is a bit annoying, because both the bisulfate and the nitrate salts are solids, and the product of the reaction, the sodium sulfate, is also a solid, so you just end up with a lot of solids needing a lot of water to keep everything dissolved. I ended up struggling to complete this distillation because I lost too much liquid and ended up with a solid mass of material. Now, I could have heated this up to about 300 C, at which point the salts would have melted together, allowing the reaction to continue. However, I didn't want to do this because I had a stir bar in the flask, and they cannot survive that temperature. I just decided to cut my losses since I didn't need all that much nitric acid anyway. So here is my product, about 50 milliliters of nitric acid. Not fantastic, but certainly good enough for what I need. I mixed the hydrochloric and nitric acid in roughly a 3-to-1 ratio to produce a weak aqua regia solution. I then heated the solution to about 80 degrees Celsius. Now for the moment of truth. Let's see if this gold bar will dissolve. At first, I didn't see any change, but after a couple of minutes, I noticed a distinct yellow haze in the water. After a few more minutes, I could clearly see the bar dissolving. It's so cool to see one of the most stable elements react like this. That aqua regia stuff sure is strong. I waited another half hour as the bar eventually fully dissolved into the acid. Now we have a solution of chloroauric acid, along with any remaining HCl and nitric acid. We need to remove those to get pure chloroauric acid. Fortunately, this should be easy enough, as we just need to boil off the other acids. I put the beaker on the hot plate and boiled down the solution as quickly as I could. Unfortunately, as the solution reached dryness, I noticed some sort of contaminant appeared. What happened? Well, you see, gold really likes being in its elemental form, and doesn't like being an ion. At high temperatures, gold compounds decompose into elemental gold. What must have happened was that as the water ran out, the temperature quickly rose from 100 degrees Celsius up to the decomposition temperature, converting us back into elemental gold. Realizing this, I decided to redissolve the gold in aqua regia and start the drying process over again. This time, I was much more careful and didn't overheat the mixture. I kept the hot plate at a gentle 80 degrees Celsius the whole time. The result was this small pool of a dark orange liquid. If I'm correct, this should be chloroauric acid trihydrate. It has a melting point of 30 degrees Celsius, so as the hot plate cooled down, I waited to see if it would solidify. Sweet. I think we did it. Now that I had pure chloroauric acid, I could add distilled water to it and make a solution. I added just enough water to make a 33 millimolar solution. From the papers I read, this solution should be more than sufficient to make nanoparticles. Lastly, we need a reducing agent, and an ion for stabilizing the gold particles. The most common reducing agent for making gold nanoparticles is sodium citrate. The citrate can pull double duty as both the reducing agent and the ion to stabilize the gold particles. Now that we have all the necessary chemicals, let's make some nanoparticles. I'm going to start by following the Turkovich method, named after the scientist who developed an easy and repeatable method for the synthesis of gold nanoparticles. We start by preparing a tiny beaker and a stir bar. We add a very dilute solution of chloroauric acid to the beaker, and we prepare a sodium citrate solution in a second container. Then we bring both solutions to a boil. We then add the boiling citrate to the chloroauric acid, and we wait. In only a couple of minutes, the solution starts to change from clear all the way to a deep purple or red, indicating that we've produced gold nanoparticles. Now, you may be wondering, why isn't the solution gold colored? Well, the reason for the red color is due to a property called surface plasmon resonance. Basically, the shape and size of the gold particles cause light of certain wavelengths to be strongly absorbed. You can even use the color to estimate the size of the nanoparticles themselves. This property is only really noticeable when the gold particles are smaller than a couple hundred nanometers. If the particles are larger, then they'll start to appear as black and then shiny gold. Based on the color, it looks like our nanoparticles are probably somewhere between 50 and 100 nanometers in size. I used a micropipette to place a drop of the nanoparticle solution onto a silicon wafer, and then placed it on a hot plate to gently evaporate the liquid, hopefully leaving behind our nanoparticles on the silicon surface. I fired up the scanning electron microscope, and I put the chip inside to get ready for imaging. It's a little difficult to see, but you should be able to spot a circle in the center of the chip where the nanoparticles are. By the way, this drop looks big on the screen, but it's only a couple of millimeters across in real life. Time for a mega zoom. Wow, those are tiny. After a lot of fiddling, I was able to just barely see them, but honestly, this isn't great image quality. It's quite likely the microscope is out of calibration. If I want to fix that, I'm going to need to start with bigger nanoparticles and work my way down. So what can we change about our process to make larger particles? Well, we've got several knobs we can turn here. We could change the concentration of the gold or the citrate. We could also change the temperature or even the pH of the solutions. I spent quite a while changing one variable at a time to see what kind of an effect it had on the nanoparticle's size. But honestly, I didn't see much of a difference. All of the solutions were pretty colorful, indicating that they had nanoparticles in the sub-200 nanometer size range. I wanted larger particles. What gives? I finally realized the problem during one of the runs. You can see from the red color that we must have very small nanoparticles in the solution. However, if you look closely, you can see a gold-colored film on the surface of the liquid. The fact that these particles are gold in color, rather than red, means that they are much larger. So what we have here is a solution that has produced both small and large particles. At first, I was happy to see this. I had finally managed to create larger particles of gold. However, I quickly realized that, despite this success, I had created a new problem. If you recall, the red nanoparticles in solution are kept separate by the citrate ions. The fact that the larger particles have fallen out of solution means that the stabilizing effect of the citrate ions is no longer sufficient to keep them dispersed. The reason for this is because as we increase the particle size, we increase the number of stabilizing ions on the surface by the radius squared. However, as the particle becomes larger, its mass increases as well, making it more likely to fall out of solution. And the mass of the particle increases by the radius cubed. So by making a particle 10 times larger, we've increased the stabilizing factor by 100, but we've also increased the destabilizing factor by 1000. So we're now 10 times less stable than before. This is why the larger particles are falling out of solution. In order to make a useful resolution target, the particles have to stay separated, so this method isn't going to work for us. So what do we do now? Well, I spent a while thinking about it, and I realized that I might be able to use this problem of the particles settling out to my advantage. Check this out. Let's say instead of making particles in a beaker, we instead mix the chemicals directly on the surface of the chip. In this case, the larger particles will form and settle out onto the surface of the chip exactly where we want them. In addition, because we are no longer relying on the citrate to stabilize the particles in solution, we are free to use a different reducing agent. I actually found that sodium metabisulfite worked well for this. I got a new chip and applied about 5 microliters of chloroauric acid. And then to that, I added 5 microliters of the sodium metabisulfite solution. After a few seconds, the drop became cloudy as gold particles began to be produced and settled out onto the surface. I dried the chip and put it into the SEM for imaging. At first, I thought it looked great. But if we zoom in, then you can see that we might have created a new problem. These particles range from several hundred nanometers to about 1 micrometer or so, which is great. However, the particles are still aggregating. This makes sense, I guess, since, as we noted earlier, the stabilizing effect of the citrate is less substantial for larger particles. So as they drift downward through the liquid, the larger particles are more likely to coalesce into clusters. However, I noticed something when I moved from the center of the drop to the edges. The gold particles near the edge of the drop were generally more sparse than the center. I suspect that the reason for this is due to the shape of the drop. If we consider a surface of the chip, then the column of liquid above the chip is taller in the center of the drop than the edge. This means that there's a larger volume of chemicals and thus a larger number of nanoparticles being produced over that surface. If that's the case, then all we need to do is reshape the drop into something flatter. I think I have just the thing. I used double-sided tape to affix the chip to a microscope slide, and then used O-rings as spacers. I added the chemicals to the surface of the chip, and then quickly topped it off with another microscope slide. If you look closely from the edge, you can see that the liquid is no longer drop-shaped. It's much more even. Alright, fingers crossed. Let's see what we have. Awesome! You can see that we have a large number of well-separated particles, up to about 1 micrometer in size. It looks like this method should definitely cover us for our mid-sized particles. The only thing we need now are larger particles, ideally up to about 10 micrometer. This is the part where I really struggled. I tried over and over again to tweak the variables in order to produce larger gold particles, but it seemed like nothing ever worked. There was this impenetrable wall at 1 micrometer that I just couldn't bust through, no matter what I did. I spent days running test after test after test, and the results didn't really change. After this much failure, I stepped back and thought more about my overall methodology. How was I actually approaching this problem? I realized that I wasn't really being scientific. I was just changing variables at random, expecting to somehow serendipitously discover something useful. But that's not what science is about. Science is about understanding enough of a process to make an educated guess at which variables need to change to produce a desired outcome. I realized that I didn't really understand in depth how these nanoparticles were being formed. So I went on a scientific rampage, reading as many papers as possible on the mechanism of nanoparticle formation. And boy, is this topic deep. However, to keep this video brief, I will explain only what is most relevant, and that is the balance between something called nucleation and particle growth. At the very instant we add the reducing agent to our gold ions, the gold 3+ ions get reduced to elemental gold. Unlike the gold ions, elemental gold is not soluble, so it doesn't want to be in solution. If the concentration of gold atoms in a particular location is high enough, then several nearby gold atoms will come together to form a new particle. This process of forming new particles is called nucleation. I've only shown 7 atoms here for simplicity, but in reality it usually takes about 50 to 100 atoms to form the minimum viable particle, with a diameter of about 2 nanometers. Once this seed particle is created though, individual gold atoms can be added one at a time. This process is known as particle growth. It's important to understand that nucleation and growth are 2 entirely different processes, and so it's possible to change the parameters of an experiment to increase or decrease the rate of either nucleation, growth, or both. The big question is this: for any newly created atoms of gold, do they undergo nucleation, forming a new particle, or do they attach themselves to an existing particle and undergo growth? If the rate of nucleation is high, then most of the gold will go into forming new particles, and the average particle size will be small. But if the rate of nucleation is low, then most of the gold will go into growing existing particles, and the average particle size will be large. So how then do we slow the rate of nucleation without also slowing the rate of growth? Well, it turns out that temperature is the answer. But wait, you say, didn't you already try that? Well, yes, but not in the correct way. You see, the rate of any chemical reaction is dependent on temperature. So decreasing the temperature should decrease both nucleation and growth, which doesn't really change our particle size. However, as the temperature falls closer and closer to the freezing point, the rate of nucleation suddenly drops extremely fast, and growth dominates. This means that if we form nanoparticles close to the freezing temperature, we should have a really good shot at dramatically increasing our particle size. In prior experiments, I had modified the temperature using a hot plate, and so I never ran any experiment below room temperature. So I never got to this section of the graph where the nucleation rate drops so quickly. So I ran the experiment again, but this time I did it in a cold environment. Now, you should never mix chemical experiments with food storage, so don't actually use a refrigerator like I did. But anyway, what I got was spectacular. The particle size was much larger than before, with average particle sizes in the 1 to 5 micrometer range, with some particles reaching 10 micrometers or even larger. Finally, it looks like I now have the means to produce particles in each of the size ranges that I wanted. And all I have to do now is combine my 3 processes into one chip. And here's the fruits of my efforts: a single chip with gold particles of all sizes, from 10 micrometers and above, all the way down to 50 nanometers and below. I was even able to use the larger particles to calibrate the astigmatism settings on my machine, allowing me to improve the image quality just enough to capture some of the smallest nanoparticles. The particles smaller than 50 nanometers are still a blurry mess, but hopefully with additional debugging efforts, I can hunt down any remaining issues and improve the resolution of the SEM, and get closer to the 5 nanometers that this machine could do back when it was brand new. In the short term, however, I'm going to follow through with my earlier promise and produce some of these test targets in order to supply them to hobbyist SEM owners. Thank you so much for sticking with me throughout this journey. I especially want to thank my patrons for their patience as I worked out all of the bugs with this process. I learned a lot doing this project, and one of the biggest things I realized was the importance of proper safety equipment. And so I'm pleased to announce that my next video will feature something that I've been wanting for a long time: a proper fume hood for doing chemistry. I actually have been working on this concurrently with the nanoparticle project, and I'm just about finished with it, so you can expect that video to come fairly soon. Don't forget to subscribe and click the notification bell to make sure YouTube puts the video in your feed when it's posted. Thank you again, and I'll see you next time.